Hello there and welcome back guys to another maths video. In this one we're looking at how to differentiate inverse hyperbolic functions. So I've written down what the inverse hyperbolic functions are. So we've got r sine, r cos, r tan or r than, and we've got all the definitions, the domains of all that stuff right there. And remember the original hyperbolic functions are sine x, cos x and than x, and all of those definitions are given on the right hand side of the page. So in this video, the objective is going to not differentiate the original hyperbolic functions. I've already got a video on that. We're going to look at how to differentiate the inverse hyperbolic functions. Now, you can brute force this using the chain rule, and of course you can literally just go ahead and try and differentiate ln of blah 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 and all that stuff, and it would work out. But there's a much easier way of doing it using implicit differentiation, and that's what we're going to do today. So we're going to get some very nice formulas for differentiation. Now you might say, what's the point in differentiating these inverse hyperbolic functions? They look really messy. Is there really a point to it? And yes, there absolutely is a point to it, because what we're going to find is the answers, the derivatives that we get are super nice, super nice. And that means that it goes really nicely the other way. So if you see an integral that's somewhat simple, it's actually going to integrate back to those inverse hyperbolic functions. I'm going to elaborate more on that at the end of the video. But let's go straight into our first one, which is going to be r sine x. So we've got y equals r sine x here. The method that we're going to do is we're going to take sine on both sides. So I've got sine y equals x. Now that I've done that, I can use implicit differentiation because I already know what sine y differentiates to. Okay, so sine y, sine differentiates to cos dy dx, and x differentiates to 1. That's implicit differentiation. Then we can divide both sides by cos y to get that dy dx is 1 over cos y. Now, technically, this is kind of okay, I suppose, but really when we differentiate something, we want it to be a function of x. So what we can do is use this identity involving hyperbolic functions to rewrite cos y as the square root of sine squared y plus 1, okay? And I'm going to explain that. I'm going to justify that up here. So cos squared theta minus sine squared theta is 1, okay? That's how I'm getting that. Okay, so all I'm doing to replace cos y with the square root of sine squared y plus 1 is I'm rearranging this. Okay, you can see that if I do that, I will end up getting the square root of sine squared y plus 1. And this identity, you can easily prove it just using these guys down here, the exponential definition, so nothing complicated. The reason I've chosen to rewrite it in terms of sine is because I already know what sine y is in terms of x. I know sine y equals x. So really what I have is that dy dx is 1 over the square root of, and again, sine is just x, so it's x squared plus 1. Now, we started with something very complicated. We started with r sine x, which, as you can see here, it's a pretty complicated definition, and we used a bit of differentiation to get actually the derivative is super simple and nice. And this is what I'm talking about with integration. When you integrate the square root, or 1 over the square root of x squared plus 1, you don't have to do anything complicated. You can just recognize, oh, that's actually just the r sine function. Boom, done. So yeah, but I'll make another video on that. Let's look at r cos now. Okay, so we've got y equals r cos x. Let's do what we did last time. So this time we're going to take cos on both sides to get rid of that r cos. And now we know the derivative of cos, it's actually just sine again. That's a really nice property of hyperbolic functions. The derivative of sine is cos, and the derivative of cos is sine. There's no minuses. So we can differentiate cos to get sine, and remember, because we're doing implicit, we also need to multiply by dy dx. And then we're going to get a 1 here. And of course, we can do the same thing. So dy dx is then 1 over sine y. And I don't really want to know what sine y is because I've only got cos y. So I'm going to use this formula once again to say that dy dx is 1 over, and what's it going to be this time? So if I get sine y on its own, I'm going to have, adding sine squared to both sides, taking 1 away, I'm going to have cos squared minus 1, and then I need to square root it. So it's the square root of cos squared y, not plus, minus 1, okay? And then, of course, from there, we can say that dy dx must be 1 over the square root. Cos is just x here, so x squared minus 1. So now we know that the derivative of r cos is just 1 over the square root of x squared minus 1. Finally, let's look at r than or r tan. So this is y equals r than x. Let's take than of both sides. So we have that than of y is equal to x. Now let's use implicit differentiation. This one's slightly harder, but than y differentiates just like how the trig one does. So tan differentiates to sec squared. So than differentiates to sec squared. So it's sec squared y, and again dy dx equals 1. And then dy dx is equal to 1 over sec squared y. Now, at this point, it's maybe a little bit tricky because it's like, okay, what do we do? We can't really use cosh squared minus sine squared because neither one of them appears. But actually, it kind of does, because if we divide both sides of that green equation by cosh squared, what we're going to get is 1 minus than squared equals sec squared. Okay, and remember guys, this is the same as 1 plus tan squared equals sec squared, but it's a minus, and it's a minus because of Osborne's rule, but don't worry about that if you don't know about that. So what can we do? Well, sec squared can clearly be replaced with just 1 minus than squared. And then finally, we can replace than with x. So we get that the derivative of r than is 1 over 1 minus x squared, like that. Cool, so now we've got all three of them. Let me just condense that down and have them all written at the same time so we can see them. So here they all are. The derivative with respect to x of r sine is 1 over the square root of x squared plus 1. The derivative with respect to x of r cosh is 1 over the square root of x squared minus 1. And the derivative with respect to x of r than is 1 over 1 minus x squared. And I've also rewritten their domains as well. Okay, so those derivatives are only defined, first of all, for sine or r sine when x is a real number, for r cosh when x is greater than or equal to 1, and for r than when the modulus of x, or the absolute value of x, is less than 1. Okay, and the reason is just because that's the same as the domains. Okay, and you can kind of see it, by the way, by looking at the derivatives too. Look at, for example, r cosh. How could x not be greater than or equal to 1? Imagine that x was equal to 1 or less than it. You're either dividing by 0 or you're taking the square root of a negative number. So that's kind of a, intuition there. But what I was saying about integration at the beginning of this video is if you were then posed a question like, what is the integral of 1 over the square root of x squared minus 1, for instance, you might try, a plethora of methods. You might try and use the reverse chain rule. You might try and use some sort of substitution, and it might end up being quite difficult. But it turns out, if you know that r cosh differentiates to this function, then it means that this function must integrate to r cosh. So it's no more difficult than just saying, okay, that's r cosh x plus c, and then you're done. So I'm going to do a video on this as well. So we'll do this kind of question and the harder ones too. But this is the idea. Now, I've not done any examples in this video. Maybe I'll do another video where I do examples of the differentiation. Don't forget that you still have to use things like the chain rule, the quotient rule, the product rule, or whatever else when you differentiate functions that involve r sine, r cosh, or r than. So if you need to differentiate something like r sine squared of x, you need to use the chain rule. If you're going to differentiate something like x times r cosh x, you still need to use the product rule. And if you want to differentiate something like r than x over e to the x or something like that, you still need to use the quotient rule. So you still need to use all the rules of differentiation. Don't forget about those, okay? So we'll do examples maybe in the next video, but for now, just deriving them. I hope that was helpful. And as always, I'll see you in the next one. Cheers.
That's just another way to say that I'm the best math rapper in the game today. It might sound vain, but it's just how I feel. And baby, I'm just trying to keep it real. Keep it real. Keep it real. That's like how I was in deep trouble with the law. He threatened government officials countless times and had been arrested even more. Was it them that got him? Was it someone else? Reality is we'll probably